Hello everyone, I'm Yang Yu from Nanjing University. Thank you for the invitation. I'm very happy to have this opportunity to share some of our experience on learning for decision making in real world scenarios. And we are going to deal with some learning tasks in a decision enabled environment. That means in that kind of environment, we are able to make some decisions, and the decisions are going to affect the environment. So when talking about learning tasks, we all know that a very typical classification of machine learning tasks into three types. One is supervised learning. In supervised learning, we have labeled data. The labeled data means that we have input and corresponding output. And we are going to learn the function between the input and the output. So supervised learning has been widely applied to tasks such as prediction and recognition. And the second type is unsupervised learning. For unsupervised learning, we do not have a label data, but we only have data instances. So we are going to discover some inner structure inside the dataset. So it can be applied to tasks such as dimensionality reduction and density discovery. And the third type is reinforcement learning. And reinforcement learning is different with unsupervised learning in that it has some feedback, but it's also different with the supervised learning in that it does not have the immediate feedback. That means we do not know the correct output corresponding to every input. And when we're dealing with decision-making tasks, reinforcement learning is the learning tool to deal with that. So what is the setting of reinforcement learning? In reinforcement learning setting, an agent, that means the intelligent system that we want to build, is put in an environment. And we do not assume that the agent knows everything about the environment, but only that the agent can see the state of the environment. For example, if we are going to play some game, we do not know how the game scores our actions. We only can see some state. That means we can see some screen of the environment of the game, and the agent can execute some actions, or we call decisions, in the environment. For example, we can control the avatar in the game, and the action or decisions in the environment can affect the environment. So the agent can observe the next state of the environment. At the same time, the environment can feed back some reward for the agent. So abstractly, the agent has a policy that takes the state as the input and output its action or decision. And the overall objective of our learning of the agent is to find a good policy. That means the policy have a very high long-term reward, such as expressed in the equation. Okay, so I'd like to emphasize the difference between prediction and decision making. For prediction, and we just said that we may use supervised learning to accomplish these prediction tasks. So for prediction, we are going to use some label dataset to tell us what is in the dataset. But for decision making, we are going to choose some goals. And how can we take every step of the action to achieve the goal is the question for the decision making. So when we apply supervised learning, we also can imagine that we have an environment and we connect the labeled data from the environment, and then we use our algorithm to build a model from the data. And the model can be then deployed in an application. So this is a very linear process. But for reinforcement learning, we use our policy to run in the environment to collect some data. And we are going then use the algorithm to learn a model from the data. After that, the model means that the new policy. So we are going to evaluate the new policy in the environment again. So we are going to collect the next batch of the data. So reinforcement learning process is not linear, but it is repeatedly to evaluate our model or our policy in the environment and to collect a new data set to update our model again. If we look at the learning objective, we may find the critical difference between the supervised learning and the reinforcement learning is that the data distribution can change or not. For supervised learning, we are going to minimize some loss function over a fixed data distribution. But for reinforcement learning, the data distribution depends on the policy that we use to collect the data. So after every step we update the policy model, the data distribution should be changed. So this is the most difficult thing, I think, for reinforcement learning to deal with. And according to the different objective, so for supervised learning, because the data set distribution is fixed, so we are going to assume that our training distribution and the test distribution are the same. So we can learn from a fixed training set and then deploy our model in a test environment. But for reinforcement learning, because the data distribution is associated with the policy, so we cannot use a fixed data set to learn the optimal policy. So the training method is by trial and error. In principle, is trial and error. Such as when we're playing the game of Go, we are going to evaluate a policy, then we are going to follow the policy to see what the outcome is. And from that data set, we are going to update our policy. Okay. So we can see that reinforcement learning can be applied to decision-making environments such as playing game of Go or playing some games. And it is very clear that these games can be formulated as a design problem. But when we look at some other tasks such as data mining and data analysis tasks, is there any decision-making space that we need to consider? For example, in this picture, this is a very typical picture that I found from the textbook. Some steps of the data mining. And then we know that the first step might be business understanding, and the second step is to understand our data and prepare our data, and we are going to model the data. And after the evaluation, the data can be the model can be deployed. So in this process, we really need some decision making techniques, and we can see that the end of this process is deployment. So the deployment means that we are going to use that model in the application scenario. So is this the end of the analysis, or is this just the beginning that our model will influence the real world? If the second is true, that means if our model we are going to affect our environment, we are going to face a different distribution of the data. So if we are considering the use of our model, then we may need to consider the decision-making effect in a larger picture. So how can the model influence the environment. Here is an illustration that our data analysis system is a doctor, and the doctor doing some health data analysis and tells me that I'm going to be ill because my health condition is not very good. When I'm hearing this result, I'm not going to do nothing. I am going to take some exercise. I'm going to take some sports to keep myself health. So actually, after 1 month, I will find myself fine at that time. But if the doctor tells me that I'm going to be fine, so what will happen? After hearing the doctor's advice, I will do nothing. So actually, after 1 month, I will get ill. So in this scenario, we'll see that the prediction is always wrong with the actual outcome. Is that the problem of prediction? Actually, the prediction is just fine because when we are using superlearning to do the prediction, we assume that the data set, the data distribution will not change. The environment will keep the same as the past environment. But actually, in our real world, we have design variables, and we can change these design variables so the environment will change. So on this situation, the prediction is just for one piece of the time, and it will not consider the design and the design outcome. So we are going to find that the prediction might be insufficient in this situation. So here's some experience that we dealing with some real world applications involve design variables. First is that we need to identify if there are some design variables in the environment. If there are, we need to consider them, but we find that some previous approaches just ignore the design variables. So if we want to further improve the performance, we need to consider the design variables. The second is that in this situation, the database evaluation can be much biased. That is because the past data will not be from the same distribution as the future data. And we do not have the future data, so we only have the past data. So we are only able to learn from the past data, which is actually very hard to achieve good performance if we only learning from data. So is there any application scenario that design variables were neglected? One example is the online e-commerce environment. In this situation, we are going to make some recommendation of items to the users. And we are going to connect some past data. This is by mastering approach that using superlearning. We collect some past data. The data are labeled by the user actions. So the input is the user features and the item features, and the output or the labels if the users bought this item or did not buy this item. So we use this kind of a labeled data set to train our model, and we use this model today to recommend some items to the user. So we are going to predict if one item is going to be bought by customer. So we are going to recommend the items have a high probability to be bought. By this way, as we actually assume that the customer's future behaviors are similar to their past behaviors. So we can use superlearning to do the recommendation. And it seems to be very natural way to deal with the recommendation problem. But actually, we can see some other phenomena that are not fitting this assumption. We know that advertisements are everywhere, right? So the left picture is from the Amazon website, and the right hand picture is Taobao website, which is very similar to Amazon in China. So we can see that the advertisement is placed at the top of the recommendation. So we all know that what advertisement is. The seller willing to pay to put the items on the top of the recommendation list. Why do they willing to do that? If we assume that the customer's behavior will not change, the advertisement will have no effect, right? This is because that the customers did not buy this kind of products. They were not going to buy this kind of products in the future. So even if we put the advertisement at the top of the recommendation list, the customer will not buy if their behavior is like the past behaviors. So actually, we can see that the sellers are willing to pay to do the advertisement. That is because they will change the user behavior. The selling of this kind of advertised products will be largely increased if they put at the top of the list. So this means that we changed something, that we changed the customer's idea. So how can we do that? This is because the prediction that we just mentioned is just one piece of this system. After the prediction, we will actually recommend the item to the user. So this recommendation is actually one design variable. Regardless of our prediction, we can decide to recommend one item or not. So this is actually the design variable. And for the advertisement actually changes the recommendation variable, the recommendation design variable. So it will change the outcome. So actually, we have the variables in recommendation systems. So we also doing some. We also have done some experiments to verify if the design should be considered in an online e-commerce environment. We have the first step to verify this is to build a very simple environment to simulate the interaction between the user and the recommendation system. So for this very simple environment, we run the learning to rank algorithm, which are a kind of super learning. And in the left figure, we can see that we actually test 5 kind of different learning to rank algorithms, and the top of the performance is about 35. And in the right hand figure, which use a reinforcement learning to maximize a long-term total reward. So we have 5 curves. They are using different gamma value. That means we consider different lengths of the horizon into the future. So we can see that for reinforcement learning, that means we are for the approach that consider design variables, the 35% performance is just at the beginning, and then we can achieve as high as 55% performance. Moreover, we can see that the highest performance is from the longest horizon into the future. So if we consider a longer return, we will receive a better performance. But this is just a verification in a very simple artificial environment. And actually, Years ago, together with the Taobao team, we actually test the reinforcement learning recommendation system online. And actually, it has achieved significant improvement in the GMV. So we can see that in this kind of environment, considering design variable can be very helpful. In this test, we actually train our reinforcement learning in a real environment. We have about 10,000 of users to help us to train our reinforcement learning. This is actually very costly. So we wonder if we can train our model from the data. So if we collect some past data which is already available, so we can save the cost for training. But when we are going to consider using some past data for do the training, we need to be very careful that the online situation might be different. Traditionally, we use some training data collected in the past to train our model, and we are going to use some validation data to validate this model. If the validation result seems to be good, we are going to deploy this model online. But if our environment contains some design variables and our model output may affect the environment. So as a result, when we are collect some past data for training and validation, the data was collected under some old design policy. That means the old situation. But when we deployed our model online, we are going to make a new situation. The data distribution may change. So the question is that the very commonly adopted approach that using validation set to evaluate our models can still be useful when we consider a design variable environment. So we together with the Taobao team, we have done some experiments to see if the validation set evaluation is still useful. Here is some experiment result. We can see that here we have some different groups of methods, and most of the methods are super learning methods. Okay, and then we use group awk or NDCG. The two criterions are from the validation set, and the last column, the true score, is from the online A/B test. And we can see that, for example, this one, we can see for the first group of methods, the group awk have the rank that the first method is the best, and this is the second, this is the worst. But when we look at the true score, and the order is inverse, we can see the last one has the better score, and the second one has is the second one, and the first one is the worst. Worst. And for the NDCG, we also see that in this group, the second method is better, okay, and then the first method is worse. But the online result is also inverse. The first method is actually better. And more significantly, for this kind of approach, this kind of approach considers partially considers the design variable. So we can see that the performance of group awk and NDCG is very worse, is much worse than the above approach. But their online test result is much better. It's significantly better than any of the above approaches. So this is we have a question that we still can still trust the validation result. So what kind of this kind of two approaches? For these two approaches, they do not use the validation data metric to evaluate a model. It uses a reinforcement learning algorithm to do the ordering of the items. And for reinforcement learning, we need some evaluation function to give the reward to the agent. So the evaluator is the key here, uh, and we can actually use the evaluator. We can actually use the supervised learning to learn the evaluator. And so what's the difference between evaluator and the data matrix? For the data matrix, we only use the validation set to evaluate the outcome of our algorithm. But for evaluator, it can actually generalize uh, to some out of data distribution and can give some score, so that if we um, generate some ordered list that were not in the data set, we can still give some scores to the can feedback some scores to the reinforcement learning. To implement this kind of algorithm, so we can actually use supervised learning to do the to learn the evaluator. But we also be very aware that when we generate some lists that are far from the um, past data, our evaluator can be of low confidence. So we use a discriminator to judge if our if our order list is far from the real data set to give a confidence. So we can use a weighted scores to train a reinforcement learning to get the result. So in this approach, we use reinforcement learning to consider the design variables, and we can see that it is very likely that the generated order list can be out of the real data. So here, even if we use an evaluator, we cannot evaluate the order list that are very different from the real data. So the ultimate way might be to build a simulator. A simulator is something that can evaluate every kind of decisions. And if we know the result of every kind of decision, we are going to find the best decisions. For the recommendation systems, we are going to dealing with some bias, and to build a simulator, the key part is to simulate the bias in our system. So actually, can we do that? Our idea is to use supervised learning to learn the buyer model. We have connected some data that a buyer has see some recommendation, and we also recorded their actions. So we can build a labeled data set about their input and the output of the buyer model, and we can use reinforcement learning to do the to learn the buyer model. However, remember that the buyer model will serve as a simulator. That means when we have the buyer model, we are going to recommend a lot of different items to the buyer, and we are going to see how the buyer reacts with our recommendation. That means we are going to jump out of the distribution of the past data. So it proposes a great challenge to the generalization ability of supervised learning. In one particular situation, I saw that it's feasible to use supervised learning to learn the simulator. which is in robotics learning environment. For this robotics animal, they used super learning from sufficient data collected in laboratory to simulate the movement of the robotic. So they can get a useful simulator, and they can train the movement policy in that simulator. That means when we can collect sufficient data about different disease and their response, we can use super learning. Even if we are facing some more complex environment, such as people are involved in the environment, we can use some complex model to fit to learn the behavior model, as long as we have collected sufficient data about the action and response. But in many real-world situations, we can only collect the action response data partially. We may not allow to try too many different decisions or actions to see how the response is. So can we learn the simulator in the condition that we can only have limited data in the dimension, particularly in the dimension of the action or the decision? So one way we find that can help us to learn simulator is we can actually infer the intention of the user so that we can augment our data. When we have collected the past data that can tell us on what kind of recommendation the user have what kind of behavior, we do not directly learn from this data a user model. Instead, we use this kind of data to infer the intention of the user. This can be done by inverse reinforcement learning. That means we treat each user as an agent too, and this agent learn their policy according to some hidden reward function. And when we see the user have some behaviors, these kind of behaviors should receive the highest score from the reward function. According to this kind of principle, we can infer the hidden reward function of the user, and this reward function can be treated as the intention of the users. After that, when we have the reward function in other for other recommendations, how the user behavior, we can generalize their behavior data by maximize the reward function. This is just similar to playing games. So from the past data that we have collected, the first step is to learn a reward function. That by guided by the reward function, we can generate more data in other kind of decision environment. So we can have some data that will not appear in the past data set. Then we can have sufficient data to build a simulator. As a result, we can see that if we learn the simulator by super learning, which is the red curve, as the distribution changes, the performance drops very quickly. But if we use the inverse reinforcement learning to augment the data set, and the simulator will generate better, even if the data was collected after 1 month to test the performance. And we can see from this picture that the red bars are the real Taobao data, and the blue bars are generated in our simulator. So we can see the trend is similar, and we try to learn the recommendation policy in the simulator. And at the first step, we learn the recommendation policy in the simulator without any constraint. we obtained 30% increase of GMV initially. So we believe that this is not possible in the real world. So we add some constraint. After that, we have obtained a 4% improvement in the simulator. And in the A/B test, we have achieved 2% improvement from the super learning. So this demonstrates a way that we can build a simulator from the data, and we can learn our policy in a simulator. In this way, we do not need a real user to help us to train the reinforcement learning agent. And by the way, we have released the Virtual Taobao simulator. And according to the strategy of the company, we cannot use full features of customers and items. So the simulator may not have the same click-through rate as the real environment. And we are building a new simulator, and it will be released soon. As a summary, in real-world applications, we need to be aware that there might be some design variables, and we need to identify if the design variables can impact the environment. If so, we need to be aware that database evaluation can be highly biased, so that even if we have a model with a high evaluation performance on the validation set, it might not have a good performance in the real world. And to facilitate the learning in the best way might be to build a simulator. And even if nowadays we may not have a very accurate simulator, we may have some methods such as the meta-learning methods that can help us to close the reality gap. That means we can actually transfer the policy from an inaccurate simulator to the real world environment. And that's all. Thank you very much.